Spack Basics and HPC Containers. Mr. Mohan Babu, HPC at AMD, presented on the Spack Basics and HPC Containers. He covered the basics of Spack, its concepts and creation, and the containers in HPC.
Yeah, as part of today's discussion, we will start knowing a little bit about Spack and HPC containers. So a brief about myself. My name is Mohan. I currently work at AMD, Bangalore location. I've been with AMD for around 3.5 years. So prior to that, I was in a cloud computing service provider startup at Chennai. So in overall, I carry around 6 years of experience in benchmarking and data analysis. So at AMD, I was part of HPC team. So here we deal with a lot of customers who are running HPC benchmarks and applications for the real time in the universities or the with OEMs. So I will also just give a brief how we adopted Spack for our workloads and how that actually changed our strategy towards HPC. So quickly into the agenda. So we will discuss why we are here today. So as part of introduction, the basics of Spack and some important concepts of Spack. So I may not be able to cover all the Spack concepts because due to time limits. Spack is very huge. It may take around 6 hours to 7 hours time to complete all the Spack topics. And one important concept in Spack called environments. And I will also explain some basic steps to create your own packages and how containerization is being evolved into HPC, and so how are these containers are being deployed in HPC currently. And I'll just give you a final conclusion about this whole topic. Okay, so quick introduction. Basically, I assume people who are here already have some little bit knowledge of HPC. So HPC is nothing but a high performance computing, which is things that cannot be done in a single computer and can needs at least 8 or more than a number of cores and high flagship cores and very good memory bandwidth and high speed network. So if you combine all of them, you can generate a HPC system. With that system, you'll be able to run some of the complex applications around the world. It can be weather forecasting or molecular dynamics or quantum chemistry applications. These applications are real-time and are being used in most part of the world, and many companies also adopted HPC for their simulations. Let's say an example of simulation is like if a car manufacturing company wants to test their ability of the car, they can do two ways. They can do it in two ways. One is build the car and do it all the test, like driving test, accident test, and the airbags opening. All these simulations they can do it on physically, so that will cost a lot of time and money. So they can also do the same thing using software, some fluid dynamic softwares. So on the HPC systems, so given the parameters, they should be able to get the expected behavior of the whole system of the machine and the car itself. So in these scenarios, software comes in handy for HPC system. So all the organizations who are adopters to HPC, they're able to generate better products and deliver better products and give the best quality of the product. So that is the overall HPC use case and requirement. So as part of that, every application might be depending on a lot of other applications as the intermediate layers to deliver final computational power of the network bandwidth power. So MFEM is one such library which actually solves finite elements, higher order of finite element problem. So to build that application, behind the scenes, that requires 31 packages and 16 dependencies. It's just like a tip of icebergs. We know only application name, but internally that requires a lot of dependencies in the package installations. So that is MFEM is one small application. If you go LBAN, which is a neural network for HPC developed by Livermore National Laboratory, that is a medium size package which requires 71 packages, 188 dependencies. And Arconda, Arconda is one of the such data analytics tool which mostly being adopted in AI that requires 179 packages and 527 dependencies. So the idea of this whole picture is to let you know, we might know the application name like NAMD or Quantum Espresso or any other HPC application, but internally to build that application and running on the HPC system, you must require all the dependencies and their linking to finally build and run the application. So we will realize only when it comes to building an application. Let's say if you want to build NAMD, you have to make sure you have a Linux system in your Linux kernel in your system, and install all the dependencies like OpenMP and FWW first. Then link all these OpenMP and FWW at the time of building NAMD. So finally, you'll be able to build NAMD. So once your NAMD is built, then you can run simulate all your application benchmarks on top of it. So this is the behind scenes, but this is very complex and tedious. If you want to generate one script based on these links, that is okay and fine as long as the versions are not changed and there is no new updates are coming in. But the HPC world is very fast moving, and there is every day there is some development is going in terms of library development as well as application development. So we must take new updated versions of libraries or the dependencies to build a latest application. For that, you again need to go back to the same script and change the variables here and there, and add the new functionalities of the application or the dependencies to get the best build out of the latest software available. That will become very tedious and very difficult to handle using scripts. So currently, and also in supercomputers, mostly all the supercomputers are using their own computational libraries internally developed for them. Like if you see Riken, which is the world fastest computer right now, and the second one is the Summit Oak Ridge National Laboratory. It is located in Oak Ridge National Laboratory. So they all have their own dependencies, libraries, compilers specific to them. So if you want to, if you have a new version of compiler library coming in, so again you have to change all your strategies and the script recipes for that. So again, there may be many variants in the sense like if you say with thread without thread, building up an application with thread and without thread, and you want a shared library or a static library, and you want ILP64 support or without ILP64 support, and you want single precision or double precision build. Based on that, you need to have a lot of combinations to build certain application. That will be very difficult on the supercomputers, because supercomputers are very costly to use. So if you spend a lot of time in installing itself, then we are wasting a lot of time and energy in supercomputer. So these are the other use cases where we actually require some mechanism that can reduce a lot of this overhead coming in building and running the applications. So just a glimpse of how it looks like, how many combinations that is possible, that needs to be addressed in the HPC world. If you just take 15 applications, and each of on an average depends on 80 software packages, and they are all the HPC clusters are hybrid, and which means you will have CPUs and GPUs together. So that has to be supported for all the platforms, and you have a lot of compilers also like Intel JCC Clam. So you need to verify other programming models of OpenMPI and OpenMP and Raja and Cocos. So all these variants are, and you can also verify the external packages that is implemented for your software. So if you combine all of them, it becomes like 1.2 million of combinations that you need to address while building an application to get to know which one is the best performant recipe for you. So if you do it manually, it will take years of time to do all these application combinations and all. So this is where we actually need some kind of automation or the improvisation to go forward. So that's when Livermore National Laboratory So so there comes a general question about why don't we just use containers just like this. Now you say 1.2 million combinations are there, so you can simply generate containers for 1.2 million combinations of recipes, and because they are all container gives reproducibility, so you can sorry, you can use the containers in HPC environment so that it will be easy for them to reproduce the performance numbers that they expect. But the problem is creating the images for each and every combination is like very difficult, and writing a container packages with each and every OS package manager is, again, it consumes a lot of memory for itself, so it is inefficient for supercomputers. So we actually, to address all the performant necessary, HPC containers needs to be rebuilt for every combination that requires. So going with only containers and manually developing recipes is also a not a feasible solution. So what should be the feasible solution? Something like Spack. Spack is a tool developed by Lawrence Livermore National Laboratory. This is an open source code. This is where what we discussed earlier. The Spack falls into the place where it tries to optimize all of the complexities available that is existing in the HPC software building and bring up. So Spack is very easy tool to use. You can just clone it and set up the environment and just try to use it without any much of complexities. So what a Spack try to do is it doesn't require much of space. It doesn't require much of prior knowledge what you have in the system. Like it, whatever dependencies you have, it will still go with that. The only requirement that Spack expect is you need to have some compiler to use any of your build to go. So it requires minimum. There are some minimum requirements for the Spack, something like Python, GCC, and some Makefile or Autotool. Any of this build system available in the Linux. So most of the Linux distributions are coming in nowadays. We'll all have all these things. So for that reason, Spack mostly doesn't ask you to install any of the other further dependencies. So it is easy to clone and grow in mode. So once you have Spack set up in your environment, installing with Spack is very simple. Just if you see here, Spack install HDF5. HDF is one of the library used for accessing a lot huge memory, huge data files, which you can be used in WRF kind of applications. So if you want to build HDF5, if you don't specify any version or something like that, Spack will have its own preferable version. It will go with that version and preferable compiler and it preferable architecture, microarchitecture. If you run it on the Intel machine, by default, it will read the microarchitecture and get the type target variable and keep it as a keep the same. Similarly, if you run it in AMD EPIC machines, based on the Gen architecture, it will try to get the target value and keep it in the target field. So most of the things are automated behind the scenes. But if you really want to have a specific target version of the HDF5, then you should pass it as a @ symbol. @ symbol is meant for the meaning of the @ symbol is to specify the version of the application or the dependency. And you can also have named arguments like C flags. You can pass C flags in the command line itself if you wish to. And the names keyword arguments, it read as keyword arguments, and based on the valid keyword arguments, it will try to build the application without much of issue. So if you want a specific compiler to be used for your build, you can use percentile symbol. Percentile symbol is for specifying the compiler. And again, a target is a one variable where it builds your binaries for particular target given target architecture. And so you have, there are variants in the applications. Let's say HDF5 can be built with the thread safe and without thread safe. If you want that variant to be enabled, you can use plus symbol. Plus symbol is meant for variants of the particular library. And similarly, if you see here, variants are like MPI is one of the variant. So when you have MPI is one of the variant, you can pass. We'll come back to that why MPI is just mentioned like this, and this considered as a virtual dependency. So we'll talk about this virtual dependency a little later. So once you have MPI as a dependency for HDF5, so to specify which MPI implementation do you want to pass on the version of the MPI implementation, you can specify @ symbol. to pass as a dependency that needs to be used for building HDFI. So so Spac is trying to solve most of the complexities in the HPC application building and installation and running. So Spac is also evolving very rapidly, and they're also contributing. I mean, they're also developing DevOps features like CI, integration, continuous deployment. They also have container support and many more, and coming in for the further versions also. So what is actually Spac Manager? Spac is a package manager. Package manager, we all know package manager. There are so many packages managers like CMake and Make. Auto tools are there. This is not something like replacement for them. This is a this can go in complement with these other implementations of CMake and Auto tools. So Spac will support all the package managers available in the HPC world, and based on all the recipes are developed. Recipes in the sense like the package which is developed for to build an application. Let's say if I want to build a NAMD, I should have a Spac recipe for NAMD. So recipe, it is nothing but a script, Python script, which is written for NAMD as a class name. And internal to that, it will have all the dependencies mentioned for it and all the versions supported and all the variants that we mentioned. And you will also have a configure section where you can pass all your configure options, and it will have steps to install. What steps to be passed, like once make is done, then make check or make install, and all these things. So that is called Spac recipe here. So it also supports all the build systems, low level and high level. So Spac also is something like maintains the cache of all the dependencies. Let's say when you are building an application like NAMD, if something breaks in the middle, so you don't need to build everything from the beginning again. So it will hold the cache of all the dependencies that are successfully built so far. So once you rerun the command, you will be able to go forward from the place where you already left. So Spac also holds cache kind of behavior. So we'll talk about that behavior a little later. So who actually uses Spac in real time? So Spac can be used by end users of HPC software. Let's say people who are computational domain science scientists. So they want only they doesn't know much of HPC system. They want only application to be installed and run without any much of complexities. So for them, they can simply use Spac, set up the Spac environment and install the Spac and install the application and use the application. So without much of hassle. And HPC application teams, people who want to develop tune the application itself, they also can use the HPC. They can also use the Spac in their HPC application, benchmarking and analysis and tuning and porting. And also package developers, people who want to contribute, develop a package for their own software, they can also be used Spac. And system administrators, people who are providing working in HPC centers, they want to there are like Linux administrators who want to provide HPC libraries and the application support to the whole team. They can also use Spac to install all the dependencies and the applications readily, so that people who are coming in, simply they can use the application and run it. So as I said, Spac is growing very rapidly. So because of the community strength, so the community coming from AWS, AMD, HPE, Intel, NVIDIA, and Riken and ARM. So they all have they're all being contributing very frequently to the Spac and developing the Spac recipes for their architecture, and improvising the existing recipes for their better for the improving in aspect of improving the performance. So AMD as part of AMD, we have contributed Broadcom packages for a compiler support for GPU, and we have raised as many as 55 plus pull requests for AMD to support AMD libraries and compilers, which is AOCC and AOCL. Along with that, we also have supported some of the applications which can give the performant recipe in the HPC in the existing HPC applications. Like we take existing HPC application and tune them for our AMD tool chain, and then update the recipe in the Spac. So HPE or Cray is using internal Spac packages for internal continuous integration. So similarly, AMD is also using something like that. So to validate support for just to make sure that nothing is breaks when a new version of compiler library releases as internal validation. So Intel also contributing on API support for all the licenses. So you can just provide a license variable in your Spac environment, and so that Intel builds will go and give you performance as expected. So NVIDIA also have compiler support currently in Spac and other libraries also. So due to this, Spac is growing very rapidly and being adopted by other HPC centers. So what makes Spac is very interesting is now what we are going to discuss. So Spac handles the combinatorial software complexity. So which means MPA is one of the dependency which actually uses for debugging of MPA applications. So MPA depends on call path and dynist and libdarf and libelf and MPA. So which library and which version of this each dependency should be taken will be handled by uh, uh, Spac internal concretizer. There is something called concretizer in the Spac, which is a core algorithm of Spac, which handles this. This creates when you just give Spac install MPA leaks, it goes and creates this DAG, direct acyclic graph, for the all the dependencies in the application. So which will internally looks like this, as like this. So Spac requires, it takes one compiler to be installed, and each dependencies will be taken and their versions will be taken by default. And there will be something called hash, which uniquely identifies each build of the dependency. So which will help to avoid any ABI incompatible issues. So what I mean by ABI incompatible issues is when you build an application like MPLX with GCC, and while the time of running, when you are trying to run it with ICC, you might face incompatible issues because of compiler used at the time of building. So similarly, these dependencies may be common for other applications also at the time of building. But when you use these pre-installed libraries or any other already installed libraries for upcoming or ongoing installation, so you might face non-compatibility between libraries. That's when Spac comes with a handy creating a R paths. So R path will tell you that where to check the dependencies for the particular application, all the dependencies. So let's say MPLX is one application. It requires call path, Redis, and all the dependencies. So R path will holds locations that are installed, all the libraries installed in all the dependencies are installed in it. So when you load MPA leaks, obviously you get to know where other dependencies are located without any further issues. So that is the beauty of Spac. It handles all the combinatorial software complexity. So again, Spac allows you to specify your version, which version is you want to experiment and try out, and which which dependencies do you want to try, and which variants you want to try. So this kind of flexibility you don't get it in other package management like tools like Easy Build or any NIX. So these other Easy Build and other things were existed earlier before Spac into the picture. But due to all this complexity, they are now nobody is using it, and only Spac is being considered for as a deployment tool for most of the HPC centers. So Spac provides you the flexibility to choose the version and the dependencies on their own version also. So as I said, it makes ABA consistency, and so you don't face any issues at the time of running your application once your build is done. So as I said, that ABA incompatibility is handled version interfaces like MPA. So as I said earlier, virtual dependency, what I mean by virtual dependency for MPA is, so when you just say MPA in the variant section, which means MPA can be implemented in two ways, either MPA CH or OpenMPA or any other. There are total 5 implementations as of now. but mostly in HPC Spac environment, we see MWAPitch or MPCH or OpenMPA. These three were the largely used. So here MPA is one, the name of the implementation, similarly like BLAS. So BLAS is a problem that can be implemented either by using AMD BLAS or Open BLAS or any other MKL BLAS. So there are so many implementation for the same problem. Similarly for MPA. So MPA can be done using MWAPitch or OpenMPA. So this kind of problem handled in as like they call as virtual dependency in Spac. So which means there is something called package.aml. In that they is clearly mentioned about MPA can be implemented any of these two things. So when you say MPA, internally Concretizer can understand that. So MPA, if you pass any of these two values, valid values, then it can understand. So any of these two are MPA implementations only. So it can go smoothly. Build can go smoothly. So so by default, if you don't specify any MPA implementation, OpenMPA is the default implementation that is being used. So even if you don't specify MPA version, like just like if you specify the caret symbol MPA at the rate 2, any MPA implementation that is above more than 2 can go and build the application. So this comes in handy for Spac. Similarly, here and we explained for MPA, this extended for other BLAS, Scalapack, all the other libraries, Scalapack, Lapack, Flame, other libraries also. So how we were talking about a concretizer, we'll just see how concretizer actually works. So when you say I want to install MPA leaks, so it will try to design a DAG for the MPA leaks and it's with their own dependencies. And when you know MPA leaks is depends on MPI. So when it comes to MPI, it has to decide which MPI to be taken and what compiler to be used for this. And when you say MPI leaks, it will decide which compiler to be used and what are the default build configurations that are required for this MPI leaks. So this is the basic DAG that creates, and Concretizer will pitch in and try to fill the gaps using by specifying the versions and the target architecture for this. And after Concretizer, it looks like this. MPI leaks by default version will be taken as 2.3 as the default one, whichever is kept as a default or preferred version. And the default compiler that is being available at the Spac environment, and the underlying architecture, whichever is default underlying architecture, it will take that architecture as a default target. And a similar that applies for the other dependencies also. If you see GCC as GCC, there is no other compiler mentioned in the Spac command. So all the dependencies will be built with GCC 4.7.3, and there is no target mentioned for any other dependencies. So all the architectures will be same. So when it comes to MPA, we already know that MPA can be implemented any of MYPitch or MPCH or MPA. So it's up to Spac to decide which MPA implementation to take. So in this case, MPCH is taken at the 3.0.4 version, and it will be, and finally this will be stored as a spec.aml for this particular build. And once your build is done, you will be able to see spec.aml on the build logs for this particular build in your install location where hashes are being used to determine. So using this hash, so I just mentioned to forgot to mention this. So hashes are very useful in the case of Spac, because when you have a certain combination, if you just change one of the version, like if you want to change libdorf, it's like if you take default version is 1 and you want to go change only version of libdorf to at the rate 2, then you will have the same build, only libdorf will be reinstalled again with the version 2, and you will create another hash value. So now you'll have two MPA leaks implemented installations available with two different hashes. So because that's where hashes are very useful here, so that it is easy to identify the differences between the installations. So Spac have so many commands, Spac to just to understand what can be built in at any point of time. So Spac spec key is one thing that lets you know what is going to be installed for you for this command. If you just see Spac, earlier we just saw Spac install MPA leaks. Now if you just remove Spac install and just keep Spac spec, it will let you know which compiler and which libraries and what architecture is being used by default. So this will help you to understand what is going to be your installation configuration likely. So if you just do install instead of spec, it will install whatever is existing in this one. So this will give you an image, this will give you an understanding of what is going to be installed if you just use this command. So this comes in very handy when you are using a larger larger Spack commands. If you see, okay, we'll come to know that complexity of Spack commands. But for example, this is the one. Simple MPLX. By default, GCC 5.3 is picked as a compiler, and architecture is picked Darwin, El Capitan. So all the dependencies like OpenMP is picked for MPA implementation, and the other call path and adaptive utils also picked. And their own versions also will picked automatically without asking from the user. So how this happens? So once you give Spack install MPLX, so some things can be go parallelly here because call path is not depending on either things. So if you see the structure here, okay, the structure makes sense for parallelization also. So it improves the build parallelization. If you see MPLX is a main, it's if you see indentation in Python, you can simply correlate from Python to here. This says like MPLX is the main package that requires two main important packages. One is adaptutils, another is the same indentation, which is call path. So these adaptutils again requires boost and OpenMP are the main two dependencies. Again, OpenMP requires hardware lock and lib access, libpca access, and libtool other dependencies. Just like the hierarchy. So when you just install, when you just make a install command, what happens, right? Adaptutils and call path will try to trigger parallel installation using fork. So other dependencies will be all the dependencies like it starts from the root, like libelf will be first installation for a lib call path. And here in this case of adaptutils, libsig sigv will be the first dependency that tries to build it. So just like from bottom to top, it goes here and there. So finally, OpenMP and Boost will be at install parallelly. Once these two installations are done, so they combine and install MPLX. They satisfy the build dependencies for MPLX and install MPLX. So this is a logical diagram that happens. What happens at the time of building an application. So when you just say install command, it will go and see what dependencies can be installed parallelly. So each dependency will have their own environment, setup environment. There they will have compiler and compiler flags. So either it is a C+ compiler, C compiler, or Photon compiler, and they have their own path variable that coming from the system environment. And they will all go into the stages like configure, make, install parallelly. And they are once everything is installed, all the dependencies are installed, then the final product will be like MPLX will be installed at the last step, and it will be stored as a different location using hash value. So okay, so there is the Spack also provides you flexibility to use the existing location installed libraries. Let's say so MPA is a complex libraries that is being used in HPC centers. So mostly nobody uses multiple implementations of OpenMPA in HPC centers very frequently. So they will have their own implementation which is optimized for their architecture. So they mostly don't want to rebuild the OpenMPA or any other MPA implementation. They just want to use the existing MPA implementation to achieve the best performance. So in that case, they can use this externally installed software instead of rebuilding the application with OpenMPA freshly. They can reuse the existing application on the system. So for that, what you can do is you can simply edit the package.yaml file and mention in the MPA section, you can mention buildable equal to false, which says that do you want to freshly build OpenMPA? No, it says if you set false, it won't build OpenMPA again. And the path, where do you find this existing, where do you want to use which OpenMP implementation do you want to consider? That will be mentioned in the here. This syntax is little older, but it's changed now. You can simply refer to the latest document in the Spack. This is old syntax, but the meaning of the syntax is same only. It will tells you where you can find the optimized OpenMP for your system. So once you specify your MPI build location in the package.yaml, when you do spec command, it doesn't show you again the hardware lock and lib API access, all these things in your spec command. It simply shows just the location available in your OpenMPA already, whatever you showed, you mentioned in the package.yaml. So other things will be same as earlier, but OpenMPA, as you mentioned, is the external package. It won't build OpenMPA again. It will just reuse from the path that you mentioned, path to external GCC, OpenMPA 2.0 in this example. So this will be your from here to the second one. This is how your latest DAG will look like, and it will save a lot of time for people. And also most of the HPC centers, as I said earlier, OpenMPA is a very complicated and complex library that is used for almost all the applications. So they want to have their optimized OpenMPA. For that reason, they mostly don't install every time OpenMPA. They will have one installation that will be used for all the application builds. So right now we have, so far we have already seen the important concepts of Spac, which is combinatorial dependency handling and external package uses and the parallel installations of dependencies. And before the concretizer, which tells beforehand what is going to be installed for you. And virtual dependency. So this, apart from this, we also have a very important Spac feature, which is Spac environment. So mostly if applications, if you don't want to use many applications, if you want to run only one or two applications in environment dedicated for your system, then environments are the right choice for you, where you can, it will not use any of your system libraries, and it will not use any of your Spac installed location. This will just isolate all your Spac environment from the existing system, and it creates a separate abstraction layer for you to understand that whatever you is installed, it is a unique installation of this particular build. So Spac AML is a file which actually holds the environment information. And when you just fire install command, it's just Spac install, whatever is mentioned in the Spac.aml will be installed in your particular environment in parallel. There will also be a lock file, Spac.lock file, which will be generated from the Spac.aml, which will clearly tells what is the hash value of the dependency, what is the version of the dependency that is used, and what are the variants that is being enabled at the time of installing any of this application building. So environments can also be used as an interactive shell. Let's say if I want to build HPL, I can create a Spac environment for HPL, and once HPL, if I mention all the dependencies for HPL like Bliss, once application build is done, I can simply execute mp-run command, which will be able to run from that given environment. So environments are very good for interactive HPC application running and building. So Spac, as I said, Spac AML holds the information of the particular project, what needs to be installed. If you see here on the right side corner, it explains the structure of the Spac.aml. So it is going to here, and it is going to install HDF5 and libelf and OpenMPA as a for this particular environment. And once this environment is created and the dependencies are built, then there is something called Spac.lock file will be generated. So this lock file will holds which version of HDFA is installed, and for which platform it is used, and what is the platform OS and other details, and compiler used. All these things will be hold Spac.lock. It will be held in the Spac.lock file. So using this Spac.ml and lock is very helpful for you to reproduce the system performance, because it holds the complete details of hashes, including hashes. So you can also, once you have Spac.ml, that you can ship that with your anyone, so they can also be able to reproduce the performance. It's just like what you have in your local setup using Spac. So this is the summary of other features in the Spac. Just like we said, you can have a Spac.ml which can be used for reproducing the performance in a better way. And you can also have your own environments which will not be interrupted by any other system libraries or the system Spack installed packages. And you can generate your own test cases for the particular application in the same environment. And Spack.ml helps you to generate CI pipeline also. You can simply convert Spack.ml to GitLab.CI.ml so that your continuous integration test can be triggered automatically. Spack.ml is also very helpful tool for containerize all your Spack implementation. If you see from left hand side, this is the format of Spack.ml. From here to right hand side, the Docker file will be created just by using one command. We will come to know that command going forward. So here are the best examples for Spack.ml. This way, Spack environments are very user friendly and interactive and has a lot of features to build Spack applications, HPC applications. So this is just an extension of previous slide. This will just tell you how continuous integration is used in case of Spack. So I'll try to, I think we're already 45 minutes. I'll try to just cover up other slides a little faster. So here the Spack 6.0.17 is the latest one, is already public release. So it has a new concretizer, which is Klingo. So they have improvised the algorithm of the concretization. So they have earlier had a default concretizer, which is based on the complete algorithm developed by LLM, but they have adapted Klingo, which is open source project. They have adapted Klingo into the Spack. Now the DAG can be prepared very effectively and easily. So once your DAG is prepared, now there's something called reuse. So let's say once you have an application installed with a lot of dependencies. So if you are going to install another application too, you don't need to build all the applications are used with the same compiler. Let's say if you are building HDFI with GCC 9.3, and if you don't use reuse, it will try to build HDFI again in case if you want to build another application too. So if you use ---- reuse, it will all use HDFI implementations available right now with GCC compilation. So that will reduce a lot of time at the time of installation. So it also have a lot of error log handling with the latest 0.17. So currently Spack supports 5969 packages, and it's still growing. I think now by the time now we are talking, it's crossing more than 6,000 also. So actually they're planning to release 0.18 maybe in this week or so. So I'll just come to one example how we can create a Spack packages. So just like as we said here, 569 packages are being already created in the Spack environment now. So creation of package is very simple. If your application is very simple, just like here, if you see Spack create, and if you pass the location of the dependency or application, it will try to understand the application and try to create a package template for you. So if you just give this command, this is the template that you get from this command, and it will have a basic Spack import Python line. Then you have MPLX as a class, which is your name of the package itself, and the MPLX is auto tools package. You can also have CMake package or Coda Mac package or Makefile package or custom package or any other package. This will tell you like it has a sections like it holds information about the package, a URL, and the description of info. And then it comes to versions, how many versions you want to you have support for your application. Then it goes to variants. You can add many variants in the after versions. Then you can also add dependencies in the later section, and you can also have conflicts. So conflicts tells you that if let's say if you cannot build AMD FW with Intel compiler, so I can mention that in the conflict saying that when you are running Intel compilers for AMD FW, don't build and just throw a conflict. So this conflict mechanism also is implemented in Spack currently. So there are so many other sections in Spack that we'll come to know deeper when you go little deeper into the application package creation. Then there comes to configure args. Internally, AutoTools package will have all the implementations like configure, make, install. So it's something like overriding. you are overwriting the configures available in the auto tools package for this particular impale leaks. So if you want to add any other args here, you can add it here as a list. And if you want to overwrite make install, if you want to specifically pass anything in the make or make install command, you can mention that as well by overwriting, creating a def make as a self and as a self method internal to the impale class. So this is a package creation example. So here are the basic commands that we actually any Spac user can will be using in a day-to-day life. Spac info tells you that application. If you just give Spac info MPLX, it will tells you where is the home page for this and what is the URL that is used and what versions are being used and what configurations are being default. It will give you the all information for the stream in this case of here. And when you use find command, it tells you install the locations of find. And Spac compilers list all the available compilers in the Spac currently. And Spac config edit compilers will give you Spac compilers.yaml where it holds the information of location of compilers is installed. And Spac edit stream, it takes you to the package.py for this stream location. And Spac spec, as we know, Spac spec just throw you output of what is going to be installed when you just pass this command stream. And Spac install, it is going to install whatever is spec shown in the previous command. And Spac uninstall stream, it will uninstall the stream and it remove all the hash value and the temporary directory stored for stream. And if you want to go to stream implementation, Spac cd -p meaning is package cd to package stream location. It takes you to stream/package.py location. And once you have a successful build, you can use cd-hi, I means installation, and go to stream installation location. And if you want to know, if you have multiple builds of stream, you want to understand which stream build you want to by looking at this stream build, you want to just understand what is the differences between stream builds. You can use LDVF. L is a long name, and D is a hash value that is used for after building of stream, and V for versions that are used for stream, and F means what flags are being used for stream building. Again, if you want to install Spac specific to version 5.10, you can use this command. We already discussed. If you want specific version, you have to use @ symbol. Specific compiler, you have to use percentage, and variants, you have to use plus symbol. And we also have keyword arguments. You can also pass this in the command line. So these are the Spac commands, and so far we discussed importance of Spac and commands that are used in Spac. So we'll come to containerization, and so what is containerization and why containerization matters to HPC. Then we'll see how Spac can help us in the containerization of HPC applications. So basically, containerization is nothing but isolating of your hardware and network and memory parts of your system, so that all the other applications can make use of the system, thinking that they are the only applications that are running on the system. So abstraction, isolation. So these are the main important features of containerization. So you can also achieve that using virtual machines. So basically, virtual machines are like having a separate hypervisor on top of whatever you have in your system, and then that hypervisor will also have hardware layer and line scanner, just like whatever you had in the system. It will also have 3 layers of application. So on top of that, you can build your application. So which is basically one kind of redundancy. You already having a Linux kernel underneath, and you still have one more Linux kernel just to support different OSs on your system on the same platform. So that is kind of redundant, which is actually, and the hypervisor is one of the important features that actually can introduce a lot of regression for HPC application. So for that reason, hypervisor and the other virtual machines are not recommended use case for containerization. So what is the best option for that? Then containers are the best suitable options. So containers are basically built on top of Linux kernel, just abstracting the file system, and they just abstract the namespaces and C groups. In case of Docker, they also generate C groups and namespaces from the root system. This doesn't require any other extra hypervisor, any other layer. They will only use the existing Linux kernel, and whatever is extra installed, like a compiler or other system dependencies, that will be getting from the container registry, and the application can be built on top of the uh, container registry image and the application. So this will try to reduce the distance from the kernel, and it will also not introduce any extra middle layer. So that's why this is an opt solution for us to run HPC applications on a bare metal. So what is good for containers? What is good for HPC in containers angle? So Docker is the most commonly used situation. Actually, Docker was synonym for containerization or most of the scenarios. Docker was a favorite containerization technique that is used in earlier of most of the HPC and computational developers. So, but the problem with the Docker is it also kind of emulates virtual machine aspects, which is something like mostly root access. Docker requires root access to run your build and run your HPC application. Docker uses Docker D, which is a root daemon, which runs in the background, which always requires root permissions to handle. It will also have access to the kernel, so which is a not feasible solution for HPC centers, because non-authorized users having access to the sensitive data may not be a feasible solution for HPC. That's why this is very negative point for Docker to be used. So National Laboratory of Livermore have developed Singularity to address this issue of the security concern. So Singularity works only with namespaces. It also it only works as a user space process, and it will not go to kernel to alter any of system access and all. So for that reason, Singularity is being adopted mostly across HPC centers. It doesn't require any access, so which minimizes security risk in the containers. So how we can generate any container image from the Spac.ml? Spac is very simple. So as we discussed about Spac environment is one great tool for creating containers or the CI tools, and also reproducing the environment also. So Spac.ml, from Spac.ml, it is a very easy single command that you can generate Docker files. In Spac.ml, if you just mention what specs to be installed in your environment, in this case, Chromax MPA, which MPACH will be the MPA implementation, and this requires CentOS 7 and this package versions. Once you have this Spac.ml package, from here, if you just do Spac containerize, get the symbol and Docker file, you will be able to generate Docker file, which exactly looks like the right-hand side one. This is the Docker file built from the Spac. Spac generates the Docker file from the Spac.ml file information. So once you have Docker file, it is very easy for if you have Docker installed in the system, it is very for us to install Docker and run the application very easily and without much of time taking and efforts. So once you have a Docker file, you can simply run docker build t target my image. Then it runs, and then once you have Docker, it takes you to the interactive mode where you can pass your MPA run command. Again, when we are discussing about the differences between Docker and Singularity, so Docker doesn't have a by default support for MPA, whereas most HPC applications are built with MPA. So that is one mismatch for Docker and HPC application. So Singularity was mainly developed with HPC application, MPA interface capabilities. That's why Singularity is being mostly adopted in HPC centers. So now coming to conclusion, so Spac is exceptionally useful tool for HPC application in supercomputer environments, and also for people who are working on HPC development and porting applications. So because Spac also is growing very rapidly because of this community that is being adopted, and the strong community from the top companies in the world, AWS, AMD, Intel, and NVIDIA. So with the needs of HPC into the cloud, as we know, cloud being adopted for HPC very rapidly nowadays. So obviously reproducibility and portability was the main concerns that are coming with this. So Spac can solve most of these issues in the cloud environment. That's why AWS is very prime partner for this Spac. They were adapted Spac to the extent where they can run HPC, they can fulfill all HPC orchestration needs in the cloud. So coming to Docker and Singularity between, so Singularity is being preferred over Docker because of the security reasons. And when you do the performance validation, you clearly know that most of the things, most of the time Singularity wins with respect to performance. Because Docker is not by default support for MPA. When you have a scale out environment, Docker may not give you the expected performance. So that's why Singularity is a preferred choice for HPC centers. Yeah, I think I'm done. I think it's exactly 1 hour. Let me know if you have any questions or doubts.
Ganesh sir, you are in mute.
Oh, okay. I'm sorry. I turned on my video and turned off. Okay. So, any questions, Sabira?
No, sir. Everything was good. I got some clarification by Morgan. He spoke me, but and he explained all the things in deep knowledge. I understand that. Anyway, the issues so far we didn't see. Anyway, we have done the Spack installation with a lot of applications recently for some US customer, right? That was done very well. Hereafter, when we get some problem, we need to contact Morgan in special, specifically when we get some technical issue. But the session was really good in theoretically.
Okay. And Shiva, do you have any questions?
No, sir.
So we got the first session from Morgan, and I think Morgan, we have to be very grateful to Morgan. Actually, he spent nearly an hour for this, and probably I want to start a group, Morgan, with this, probably inviting more people, and let's
Okay.
let's work on this. And I'm happy that you covered the summit system also. That's a system we built in 2017-18 in Oak Ridge Lab, and I was part of the team. So
Okay.
I did if you would have seen my WhatsApp display also, like the DP, so that system with the system only my photograph is there. So that's real. That's not a whatever the graphics image.
Okay.
So yeah, I'm very happy to know that, and certainly we have a lot of other people also to be part of this. We have Dr. Samir from Oak Ridge National Lab. I mean, not Oak Ridge, University of Oregon, who is expert in E4S. I will also bring him later on to this kind of the event and talk about it, and probably we'll create a WhatsApp group and see how we can take this group forward. Okay.
Sure,
and also
sure.
We'll talk in person. Yeah, we'll talk about various things whatever available around this. Okay. Sure. I think yeah, this is good. Any other questions, team?
No, sir. Thanks, Morgan.
Okay.
I appreciate your the presentation you did. That was really good. Thanks a lot.
Okay. Thank you for all participating this this workshop. I mean this webinar. Thank you, and let's look forward for another webinar soon. Thank you very much. Thank you, Morgan, again. Thank you.
To get instant updates, follow us on our social media pages.